Hello, and welcome to this presentation for the ISC 2020 Digital Conference. My name is Ryan D. Lewis, and I'll be presenting this conference poster, Log-Based Fingerprinting of HPC Applications. The research behind this poster is conducted at Argonne National Laboratory under its Leadership Computing Facility and Data Sciences and Learning Group, and at Northern Illinois University's Department of Computer Science by myself, Dr. Zhengchun, Dr. Raj Kettimuthu, and Dr. Michael E. Papka. The goal of this work was to gain some insight into how the scientific community is leveraging leadership supercomputers using data encapsulated in scheduling and performance logs. We performed data analysis on logs collected from Mira, a supercomputer at Argonne's Leadership Computing Facility, and engineered features to fingerprint HPC applications based on this log data. These logs include scheduling, task history, autoperf, which is a logging tool for MPI communications, and Darshan, a logging tool for file I/O. As you can see from the two figures on the right, a handful of users and applications account for the majority of Mira's core hours usage, and so we focus on exploring the patterns of usage these users and applications exhibit. Usage patterns of applications on Mira appear to be more pattern-laden or repetitive than many other leadership resources, a trait which we take advantage of in much of this research. One avenue we explored is the viability of using performance logs to positively identify executables based on their performance characteristics. We identified 7 features, either engineered or from the logs, which yield the strongest predictive power. These are the fraction of runtime spent on inter-process communication and file I/O, the achieved operations per second and floating point operations per second, the number of processes per node, and the average RAM fetch and store per cycle. The 2D t-SNE embeddings at the bottom here show applications graphed based on these 7 features, where each color represents an application. As you can see, clear clusters emerge for many of the applications. Using these features, we were able to achieve greater than 99% accuracy in identifying top core hours consuming applications with both XGBoost and neural network-based models. Another avenue we explored was the use of this log data to improve application runtime prediction. Better runtime prediction has potential benefits for job scheduling on leadership computers, but is limited due to its reliance on the information available at submission. We suspected that, since many of Mira's top core hours consumers have relatively repetitive usage patterns, we might see some success training accurate models where similar efforts on different leadership resources have failed. As you can see from the 2 t-SNE embeddings shown here, the more sparse information available at submission time makes for less apparent clustering and a very challenging learning environment for our models. Since underestimating a job's runtime can lead to extremely negative outcomes, such as prematurely killing a job, accuracy is extremely important. We do see that by adding a sort of margin time or safety buffer to our predictions, it's possible to mitigate the number of underestimated jobs while still providing beneficial estimates for others. The optimal margin of error, or the optimal margin time to add, likely depends on a variety of factors, but you can see some example times and their effect in the table shown here. This work provides leadership computing facilities with the potential to verify the identity of applications using their resources and audit their usage, as well as the possibility for improving the efficiency of job scheduling and reducing queue times. Our work with performance log analysis is ongoing, and even with the sunsetting of Mira at the end of 2019, we believe valuable insights can still be gained from the data collected on Mira, as well as other supercomputers at ALCF and other leadership computing facilities. We are currently exploring the use of additional logs to improve model accuracy, the viability of hardware performance counters as a lightweight stand-in for more heavy-handed performance logging tools, and the expansion of our fingerprinting techniques to more general categorization and classification. If you have any questions for the authors about this poster or our research, please feel free to contact us by email. Thank you, and have a good day.